Hello, my name is Ryan Alvarez, and I'll be presenting on the Zener diode project for EEE 536 semiconductor characterization. My other two team members, Byron and Afi, will be presenting later on in this video. The focus of this project is to precisely model and simulate the Zener diode, including the effects and electrical characteristics using Silvaco ATLAS software. In a regular diode, current can only flow from anode to cathode. In a Zener diode, current can flow in the reverse bias direction when the reverse breakdown voltage is reached. In the diagram below, you see a Zener diode with a reverse breakdown voltage of 10 volts connected to a 5 volt power supply. Because the breakdown voltage is not reached, current does not flow. In the second diagram, the same Zener diode is connected to an 11 volt power supply. Because the breakdown voltage is reached, current flows. The voltage across the diode cannot exceed the breakdown voltage. Because of this property, Zener diodes are useful as voltage regulators and overvoltage protection circuits. In this project, the breakdown voltage will be determined by simulating the reverse bias.
Hello everybody, my name is Byron, and I'm going to be going into a detailed explanation of our project of building a Zener diode. So the idea behind the structure of a Zener diode is fairly trivial. What we want to do is we want to build a regular diode from a p-n junction, but we're going to change its intrinsic properties to obtain a controlled breakdown. Most p-n junctions will only allow a very minute amount of leakage current across its depletion region in reverse bias. But this phenomenon, like most things in physics, does have a limit. At a certain level of reverse bias, the p-n junction will fail and the current will be able to breach the junction. This generally happens at very high voltages and generally leads to catastrophic failure of the device. But what if we could control and use this limit to our advantage? Well, that's the purpose of the Zener diode. Because we have controlled breakdown, we're also going to want to lower the breakdown voltage so that we can use it in normal lower voltage applications. As you can see from the image on the slide, normal p-n junctions have a breakdown voltage up to and many times exceeding 50 volts. But what if we have an application where we want to use the Zener diode in a much lower reverse bias voltage? Well, luckily, the Zener diode can actually be designed for high voltage applications, yet still be scaled all the way down to a few volts. So our group started this project with many various research endeavors, and what we found is that the design of the Zener diode is reported to be centered around the doping concentrations in the silicon. Essentially what happens is that the very heavily doped P and N regions, along with some very careful engineering, creates a very, very thin depletion region, generally much less than a micron. This thin depletion region creates a huge electric field in a very confined space. So the depletion region in the reverse bias becomes so thin that it allows electrons to tunnel from the p-type valence band over into the n-type conduction band. Now, some Zener diodes, especially those used at higher voltages, also use the avalanche effect, which can achieve the same results. So Silvaco had a great example of the Zener diode. Unfortunately for us, that example was already fairly well optimized, but everything can be improved upon, so we did. We took the example diode and we changed all the parameters that we could. So first, we ran n-type doping simulations, as many intervals as we possibly could, from 1 × 10 to the 15 atoms, all the way up until the silicon became degenerate. We followed the exact same process for our p-type dopant, and then when we finally found those optimum results, we decided we wanted to test some other dopants in our diode. On our N side, we ran simulations with antimony, phosphorus, and arsenic, and on our P side, we used boron, aluminum, and gallium. What we found was that the material in our N-type doping didn't really have a large effect on the breakdown voltage or our IV curves. But for the P-type side, boron took the crown for the lowest breakdown voltage. Lastly, we played around a little bit with the P-type diffusion parameters to get a nice looking product. Our diffusion adjustment ultimately raised our breakdown voltage by a little bit more than half a volt, but our IV curve looked beautiful. It had a flatter low voltage leakage current and a much smoother transition to breakdown. And it also had a current limit to ensure recovery. With our final parameters optimized, we still had to make sure that this thing was still acting like a diode. It couldn't only be good for reverse bias, so we ran simulations across the first 5 volts in forward bias. We got expected results, as you can see in our slide. With both of our curves looking as expected, and with a decent breakdown voltage and a solid breakdown limiter, we wrapped up our data and concluded our findings. So here you get to finally see our final design. We used 5 × 10 to the 18 atoms per cubic centimeter of phosphorus dopant and 5 × 10 to the 17 atoms per cubic centimeter of boron dopant, which we diffused into our N-type substrate for 25 minutes at 1025 degrees Celsius. We achieved a breakdown voltage of just over 6 volts. So this could be something that we could use as a shunt voltage regulator for, say, a phone charger, which is a 5-volt DC power supply. And looking over at our graph, we have a nice, smooth, and predictable reverse bias IV curve with a proper recovery limit. Thank you.
Hello everyone, my name is Afifa. As you can see on the slide, these are our tasks that we split out in our major milestone that I will identify further in next slide. We have broken them out into the responsibility of each person in a timeline compared to the previously provided schedule. The team was able to complete each task within the schedule. The only change that we made to this timeline was adding the final report due date, and we assumed it's going to take about 12 days starting from tomorrow. Conclusion. The goal of our project was to create a Zener diode by optimizing p-n junction intrinsic characterization to control the breakdown voltage. As Byron and Ryan explained in previous slides, the Zener diode permits current not only in forward direction, but also in reverse direction when the voltage is greater than the breakdown voltage. In a case of large forward bias, there are some voltage drop across the diode due to its p-n junction built-in voltage and internal resistance. The amount of this voltage drop, depends on the semiconductor material and the doping concentration. The obstacles that our team faced were simulating various doping concentration and dopant material both for N-type and P-type. As a result, the doping concentration and dopant material changes in N-type did not make the most significant change in a low breakdown voltage, whereas the P-type doping concentration and dopant material made the most significant change. The Zener diode usually has about 1.2 volts up to 200 volts of a breakdown voltage, depending on what kind of a Zener diode it is. But in our case, the breakdown voltage was optimized to be about 6 volts. In summary, we had a successful project, and the remaining work of our project will be completing the final report. Thank you for listening.